Hello, everyone. Today we will be discussing the topic of binomial distribution. So let's straight dive into the topic. You should have a basic understanding of probability before this topic. So if you don't, I suggest you to just watch the basic video of probability and you'll be fine. Okay, now a binomial distribution. Why I wanted you to have a basic understanding of probability, because it is a discrete probability distribution. It helps you with probability and a discrete one occurring in clear steps. Okay, so the discrete random variables, they follow binomial distribution, right? In terms of counting the number of successes, that how many times you're satisfying the outcome you actually wanted. You're getting the outcome which you actually want. It has to, in order to it be a part of binomial distribution, it has to satisfy the following condition. There should be fixed finite number of trials, which are represented by n number of trials, and the outcome of each trial is independent of the outcome of the other trials, right? So that means it cannot be without replacement. It has to be with replacement. You're replacing everything again. The same conditions are being followed for all the experiments. Then the probability of success is also constant. And how do you represent a binomial distribution? You represent it in this ways. X follows a binomial distribution, right? N represents the number of trials which are fixed, and P represents the probability of success. Obviously, if P is the probability of success, the probability of failure would be 1 minus P, which is denoted by Q, right? And if you want to find the probability of R, right, probability of any number R, R here represents the number of successful trials. So if you want to find the probability of the number of successful trials, how do you go by it? Where R is the number of successful trials, NR. So this is basically NCR, N combination R, right? You'll have a function in your calculator of C, right? You can use that. NCR multiplied by P raised to the power R multiplied by 1 minus P raised to the power N minus R. Here, P raised to the power R means basically P is the probability of success. So you're multiplying this probability the number of times you have achieved success. And obviously Q, that is 1 minus P, is the probability of failure. So if there are N trials and if R times you have achieved success, N minus R are the number of times you haven't achieved success, you have achieved failure. So in that case, those many times you need to multiply the probability of failure, right? Now, population. Okay, now let's look at it from here. Okay, basically, right. Now let's look at it that P to the power of R, if I expand, right, P plus Q into N, where Q is equal to 1 minus P, this shows the link with the binomial expansion, right? You can see this with binomial expansion even, right? Now let's look at the important properties of a binomial distribution. What are some of the properties of binomial distribution? Okay. The expected number of successful trials is N into P. That is the mean. Okay. And the variance is N into P into Q, right? N into P multiplied by 1 minus P. And square root of this would be the standard deviation, obviously, right? Now, if the number of successes, X is the number of successes, and if Y is the number of failures, right? So we will say that X follows a binomial distribution, with n number of trials, P the probability of success. Now here Y follows because Y is the number of failures. Now our failure is actually our favorable outcome. Right? We are looking for failures. That means if we find a failure, that is our success. So Y follows a binomial distribution, n number of outcomes, and 1 minus P is the probability of the failure, which is now a success for us. Now, if the P is close to 0, then you should expect that the graph has a tail to the right. You can see it in the diagram I'm going to show here. It's tailing to the right. It is right-tailed, right skewed. What is happening? Because your probability is very close to 0. That means the majority of the, out of the 10 observations, majority of the observations, they lie on the lower end. Right? They have a lesser probability. Okay? Okay. If the P is close to 1, then the graph has a tail to the left. Right? Now it is left skewed. And if P is close to 0.5, then the graph, you will find a roughly symmetrical graph. Right? Because your probabilities are evenly distributed. And if the P is equal to 0.5, then the graph will be perfectly symmetrical. Okay. Now we look towards modeling with binomial distribution. How do we make a model of binomial distribution? Right? You have to identify the trial in the scenario, right? For instance, checking hair color, flipping a coin, rolling a dice. You need to identify the successful outcome. What is the successful outcome? In the case of flipping a coin, maybe getting a tail, rolling a dice, getting a 6, checking hair color, having black hair. And then you have to clearly state your random variable with your number of observations. Now, what kind of situations you can model using a binomial distribution? It has to satisfy the 4 conditions, right? What were the 4 conditions? If we go back, here, right? Fixed finite number of trials, independent of each other, exactly 2 outcomes, success or failure, and probability of P is constant, right? So let's look at this example. Let T be the number of times a fair coin lands on tail when flipped 20 times. Finite number of outcomes, only 2 possibilities, a success or a failure. Either it lands on a tail or either it does not. The probability is the tail is fixed, right? It's 1/2. The 4th one, independent. Each time flipping the coin, it does not affect the subsequent coin flip. Right? Now, sometimes it might seem like there are more than 2 outcomes. For example, let Y be the number of yellow cars that are in a car park full of 100 cars. Now, there are more than 2 colors here in this case. But we are only looking at 2 possibilities. There's a difference between 2 colors and 2 possibilities. We are only looking at yellow. Yellow is our success, not yellow is our failure. 2 outcomes. Rolling a dice. There are 6 different outcomes. But if we are looking at success as getting a 5, then getting a 5 and not getting a 5. These would also come under being modeled using a binomial distribution. Now, what cannot be modeled using a binomial distribution? When the number of trials are not fixed, for instance, the number of emails being received in an hour, they can be as many. That is Poisson distribution, which we will discuss later in some other video. I'm going to teach that, right? Number of times a coin is flipped until it lands on head. Until you get a successful outcome, you simply do it. Again, not fixed. Okay. Anything where the outcomes are not independent. They're dependent on each other. One trial is affecting the other trial. I gave you the with, I told you about with replacement and without replacement. So in which there are without replacement. Number of caramels that a person eats. Now it cannot be replaced in the sweet bag, right? Because a person is eating. So then it becomes dependent, right? Because then the total number of outcomes also change, and obviously favorable can also change. If you eat a caramel first, you'll be left with lesser caramel sweets in your bag. Now, when there are more than 2 outcomes, a person's shoe size, multiple outcomes, number a dice lands on. Previously, I gave an example of you whether the dice lands on a 6 or not. That was 2 outcomes. But if you're just simply looking at the number the dice lands on, then obviously. Okay, anything in which the probability of success is changing. Right? Like for instance, this is a very good example. The probability of swimming a lap in under a minute will decrease as the person will get tired. Right? Now let's look at a question. A fair coin is tossed 20 times, finite outcomes. Number of times it lands heads, only 2 possible outcomes, head or not a head, right? Probability of head, it's a fair coin, that is 1/2. Define a suitable distribution. You're going to say it will be binomial distribution. You're going to mention all 4 of the things, why it is a binomial distribution. The trials are also independent of each other. Find the probability that the coin lands heads up 15 times. So P, X is equal to 15. So 20 CR 0.5 to the power of 15 multiplied by 0.5 to the power of 5. NCR, either you have this function in the calculator or you can open it as n factorial upon r factorial multiplied by n minus r factorial. And that is how you can get the probability of getting ahead. Now let's move towards the next topic, calculating binomial probabilities. We've just looked at one example, right? We saw n is the number of trials, p is the probability of success. So, but now we will look at binomial probability distributions. Now let's look at this. We already looked at how you can find for, a single probability. Now, when you need to calculate probability of x less than equal to x, that is, you have to find a cumulative probability. Right? Either some calculators, they give the function, right? Or otherwise, what you can do is you can even, for this, the lower is 0 and the upper is x. So you can add all of them, 0 till x, because x is even included. In this case, it is P, probability of x greater than equal to x. So here, what you can do is, since you cannot have an upper bound, right? And n is your upper bound, but sometimes if n gets difficult, either you can go from x till n. The other way would be 1 minus probability of x is less than x. And what will be x is less than x? You go from 0 to less than x, right? This is, I'm just helping you in finding out the probabilities, right? If you want A till B inclusive, so you add all the probabilities of A, after A, B, all of them, okay? So this is how you basically calculate the probabilities for binomial distribution. Thank you so much.